So now it's time to really think, okay? But let me try to refresh your memory. As you think, let's go over this entire thing up to now, okay? So I'm using the PowerPoint. So initially, we have the equivalent circuit model, and we wrote down KVL, KCL equations, okay? So in the phasor domain, we simplified things, okay? So we don't like to work with differential equations. So in the phasor notation, we have very beautiful multiplication, okay? And then eventually, we didn't know how to solve this one because on the left-hand side, voltage, current, so we performed another differentiation. So now we can replace di dz with a former equation. So now we have this. So we proved up to now both voltage and current are traveling waves on the transmission line. And then somehow we define this gamma, right? This complicated stuff is actually telling you how the wave is propagating on the transmission line. Now, if you really want to ask yourselves the physical meanings of gamma, loss, and the effective wavelength, beta is 2 pi divided by lambda. So this tells you, even though you have the same operational frequency, but if you're working on two different transmission lines, the attenuation coefficient and the effective wavelength will be very different, okay? So, for a given transmission line, you would have its own resistance, inductance, conductance, and capacitance. So all these four parameters is simplified and gathered to give you a sense of how fast the voltage and current are attenuated and what are their resulting wavelength. The wavelength can be very different as compared to the same frequency wave traveling in vacuum. Okay. Now, another physical sense. Even though we have four unknowns, V0 plus, V0 minus, I0 plus, I0 minus, which we don't know how to solve for now, but there is one happy thing. What is that happy thing? There's one happy thing embedded in this equation. No matter how its voltage or current, positive propagating or negatively propagating, they are all having the same propagation behavior. They share the same gamma value. So this is telling you voltage and current, they have the same attenuation coefficient and they have the same effective wavelength on the transmission line. Right? So it's very important. Once you have a well-defined transmission line, it tells you the voltage and current are actually traveling at the same speed, traveling with the same wavelength. They're traveling with the same attenuation, no matter which direction they're traveling. This applies both to current, voltage, positive propagating, and negative propagating. Okay? So this is the only nice thing that we can up to now. Right. So these two equation sets tell you counter-propagating waves are allowed. You can have forward propagating and backward propagating. This means the transmission line can be used for bidirectional communications. This is also nice, right? So if you have a transmission line, the power can be delivered from the source to the user. The user can also somehow donate energy back to the source. Okay. Second physical meaning is, just as I said, counter-propagating waves, no matter its voltage or current, they have the same propagation constant. So that's nice. If the forward propagating wave and the negative propagating wave can have different propagation constants, that's too messy, right? And it's impractical, unphysical, right? So now we are in the process of simplification and reducing the number of unknowns. So let me plot a line. So reducing the number of unknowns. Starting from now on, it might be purely mathematical, but I'm trying to turn the mathematical derivations to really physical senses. Okay? But the overall target is we have 4 number of unknowns, which is unsolvable, but eventually we can understand what is happening on the transmission line. But that requires mathematical skill and more physical understandings, right? So let me ask you one question. I want to perform some kind of definitions. I want to define some more variables to help me reduce the number of unknowns. Does that sound reasonable? I'm introducing one more stuff, and that could help me reduce the number of unknowns. Sounds like a contradiction, but that's what happens in engineering. Usually you introduce more complexity, you gain more functionality, right? Okay. So, what I want to do now is I want to introduce a new variable called characteristic impedance, 特征阻抗, characteristic impedance Z0, hoping that it might help me reduce the number of unknowns. So Z0 is really trying to ask, okay, from above, we learned that on the same transmission line, voltage and current, no matter forward propagating or negatively propagating, they have the same wave behaviors. They have the same loss, they have the same effective wavelength. So the question is, V0, I0, voltage and current, they're divided into forward and backward. Are they really different? If they're not really that different, then I can somehow simplify them and reduce the number of unknowns by half. So I can start with 4 and I come up with 2. So the question is, if I define impedance by definition is voltage divided by current, just like resistance. But when you have a complicated circuitry, you have RLC, you have impedance, right? This is the formal definition. Voltage divided by current is impedance. So what if I try to define the forward propagating voltage amplitude divided by the forward propagating current amplitude? that gives me some kind of impedance value, which is completely determined by the transmission line. Then I might have the possibility to reduce the numbers of unknowns. Okay? Now, at this moment, you might also want to guess, is it possible that V0 minus divided by I0 minus is also equal to that? Take a guess. But can you see what I'm trying to do? If voltage and current amplitudes are somehow linked together through a constant, then that constant is provided by the transmission line. Once you have a defined transmission line, it already satisfies voltage and current is obeying some kind of specific situation or value, then you don't really view this as a new variable, right? If this is true, you only have V0 plus and V0 minus. I0 plus, I0 minus are actually known. Right? So that's the thinking. So the thinking is, by introducing characteristic impedance, can I reduce the number of unknowns to only 2? Of course, this remains a big question mark. We don't know up to now. Okay. But if it works, immediately the number of unknowns is reduced from 4 to 2, which is more solvable. Okay, so do we agree up to now? Do you understand my physical flow? The process flow is trying to define some kind of intrinsic parameter determined by the transmission line structure. And then I can view current as voltage, but having only a linear relationship. If you multiply the voltage by some constant and you have the current, then you only have to worry about solving voltages or only solving the currents. Okay? In the end, you only want to solve for 2 unknowns. Okay, so if that is my goal, where should I start? Where should I start? This is the position I should start. This is the generalized solution form, right? I have the wave equations and I have the solution forms. If I have the solution forms, I should start from there and try to really find my solutions. Okay, so where do I start? From here, I can somehow write V, Z. This is tricky. I have the generalized solution form, and I really want to rewrite it so I can really solve for the unknown parameters. Can I do this? Can I do this? Voltage phasor as a function of space can take on a forward propagating solution and a backward propagating solution. Can I say that, well, I only care about the total voltage. So even though on the transmission line, I have forward and backward, but when I add them together, they're also a solution for it, right? Superposition. When one of the component is a solution to the wave equation, I add them up linearly. This is called linear superposition. The result is still a solution to the initial wave equation. So this is valid. And this really saying that on the transmission line, at the same time, simultaneously, I have forward propagating wave plus a negatively propagating wave, which is completely valid. Okay. And I of z can also have forward propagating component and backward propagating component. Are we feeling happier? Alright, so these are the really generalized solution form on the transmission line. What can I do? Let's come back. Let's come back to the initial two equations. The one derived from KEL, the one derived from KCL. These two are very important. These are the starting equations. Initially, we didn't like them because on one side, I have voltage, which is to be solved. But on the other side, I have current, also to be solved. So initially, I didn't like these two equations. Different parameters on different sides of the equation, we don't like. But now, for this purpose, we will try to like them, okay? Because if I perform differentiation in space to V using that generalized solution form, I can immediately link to the current mathematical formula. So let's try to do it. Let's try to perform one spatial derivative, and then we can somehow combine and look at the resulting relationship, and then we can define the current amplitudes. So if I have enough space, okay, so dV of z dz equals, I'm really trying to perform a differentiation. Negative gamma plus gamma v negative. I hope this is fine for you. Can you still read these letters clearly? So after performing spatial derivative to the generalized solution form for the voltage, don't ever forget that is equal to something we already know in the form of current. Negative, right? So let's come back. Or just let me try to come back to the equation. Do I have an equation on the PowerPoint? Yeah, this one. Right? So dV dz equals negative something current. So all I'm trying to do is I'm using my solution form, and I'm using the solution form, right? Counter-propagating waves, perform its spatial derivative, and that would be equal to the negative of this one multiplied by the solution form of I. I performed the spatial derivative, this is what I have, and that is equal to negative r prime plus j omega L prime, and multiplied by my current generalized solution form. And now I can do turn-by-turn comparison. The ones with exponential negative gamma z should be compared with their corresponding amplitudes. The ones with positive exponential gamma z should be compared So I can see even the TA and the video filming staffs are tired. So let's take a 10 minutes recess and come back. But during this 10 minutes, try to write down the further definitions or the relationships using characteristic impedance. Okay, let's see you back in 10 minutes.